Hello students, I am SANJIT. This is my YouTube channel. If you see the next videos, then please subscribe these channels. So in the previous class, I was already discussed laws of reflection, laws of refraction using Fermat principles. Today I have discussed about cardinal points. Cardinal points are lie on the optical axis of the optical system. So each point is defined by the effect of optical system has on rays that pass through that point. If the rays are pass through that point, then it will be defined due to the effect of optical system. So there are 6 points, but 3 pairs. That is first and second focal point, first and second principal point, first and second nodal points. So today first we are discussed about focal points. So focal points are the pairs of points lying on the principal axis of the optical system and conjugate 2 points at infinity. These are the 2 points. Focal points are first focal points and second focal points. Both are conjugates. So it is lie at infinity. So today first discussed first focal point. It is also a point on the principal axis of an optical system, but this point is placed on an object space, so that if the ray is starting from this point, after refraction through the optical system, then the rays are parallel to the principal axis. This is the first focal point F1. This is the rays. If the ray B rays passes through the focal point F1, this is the optical axis. After passing the focal point, this is the first focal point. If the rays passes through the this point, then this is the optical system. After refracting the optical system, then this ray is parallel to the optical axis. And also the plane normal to the principal axis. This is the plane. A plane normal to the principal axis and a passing through focal point is known as first focal point. So what is first focal point? If the plane is passing through the first focal point, then it is perpendicular or normal to the optical axis. Then this plane is known as first focal plane. Then the second cardinal point says second focal point. So it is also a point. Look at the second figure. It is also a point, but this point is lie on the image space. So if the ray is parallel to the optical axis, after refraction, then the rays meet on a optical axis at a point. This point is known as second focal point. So second focal point is a point on the principal axis in the image space, so that the ray parallel to the principal axis from an object space after refracting through the optical system. So what is the definition of second focal plane. This plane is also passing through the second focal point, and it is also perpendicular to the or normal to the optical axis. Then it is known as second focal plane. Then the next one is the principal points and principal planes. The principal points also, the principal points are two types. One is first principal points, then second one is second principal points. It is also two planes, first principal planes and second principal planes. So look at the figure. This is the optical system. So x dash is the principal axis. Let us first consider a ray. This is the incident ray. The ray name is AB. So if the ray AB is incident on a optical system at a point B, then it will be refracted and after transmitting, then the ray is CF2 after refraction through the optical system along CF2 and meet the principal axis at a point F2. So this point is known as a second focal point. The incident ray, this is the AB incident ray, and it is also the emergent ray CF2. Both are introduced or both are intersect at a point S2. If the ray AB, if the optical system is not in front of incident ray AB, then the original ray is this is the original ray, and this is the emergent ray. So if the emergent ray is backward, then it is meet at a point S2. So the plane through S2 and perpendicular to the principal axis. This is the plane. It is passing through the S2 point and also perpendicular to the principal axis x dash. Then this plane is known as second principal plane, and its point of interaction P2. This plane is passing through normally to the x dash principal axis at a point P2. This point is known as second principal point. Similarly, we consider if the ray is passing through the first focal point F1. This is the incident ray F1D. If it is an incident on an optical system, then it will be refracted. The refracted ray is D and the emergent ray is L. So similarly, the incident ray F1D through first focal point F1 and the corresponding emergent ray is L. It is also, I am already discussed. So if the emergent ray is L is backwarding and also F1D is forwarding, then it is meet at a point H1. The plane through H1 and it is perpendicular to the x dash at a point P1. This point is known as first principal point, and the plane is passing through the point H1. It is known as first principal plane. Similar case of nodal points and nodal planes. So the nodal points are also a pair of conjugate points. it is also lie on the principal axis of the optical system. But in that case, the linear magnification is 1. So first we consider a incident ray directed toward the nodal point, and it will be emergent parallel to its original direction. This is the emergent ray. It is also parallel to the incident ray. So N1 and N2 be the nodal points. Emergent ray is N2Q. It is also parallel to the incident ray Pn dash. So planes passing through the 2 points N1 and N2, and it is perpendicular to the x-axis, that is the principal axis. It is also known as nodal planes. This is the first nodal planes, and this is the second nodal planes. So now let's discuss about dispersion. So what is the dispersion of light? We already know that when a white light beam is passing through a prism, then it is splitted into the 7 colors, constituent 7 colors. This is called dispersion of light. This is the prism. The refracting sides, two types, the two refracting sides. One is AB and another is AC. We also incident the light beam to the side AC or AB, but in this case, first we consider a source S. The white light is emitted from the source S, but it is converted into beam due to the slits. This is the slits. So if a beam of light is incident on one face of the prism, that is the two refracting faces or incident faces, AB or AC, but in this case AB is the one face of the prism. So the light is incident on the face AB. Then the light emerging out to the other faces like AC into the constituents colors. This is the 7 colors. First one is red, orange, yellow, green, blue, indigo, and the last one is violet. So this image of color is produced in the screen. This is the screen. So Cauchy's obtain a formula for the refractive index mu of the material of the prism in terms of wavelength. So Cauchy's derive a formula between refractive index mu and wavelength lambda. Mu equal to A plus B by lambda square plus C by lambda part. A, B, C are called constant. A, B and C are constant due to the Cauchy's. This is introduced by Cauchy's, so it is known as Cauchy's constant. And lambda is the wavelength of light. But we know that the wavelength of violet color is less than the wavelength of red color. If the symbol of wavelength is lambda, for red color the wavelength is lambda r. For violet color the wavelength is lambda v. So we know that the wavelength of violet color is less than the wavelength of red color. So symbolically it is represented as lambda v less than lambda r. But in the Cauchy's formula, mu is inversely proportional to the lambda. So if mu is increases, refractive index is increases, wavelength also decreases. So lambda v less than lambda r, then mu v greater than mu r. But for this small angle of prism, this is the angle of prism. If the angle is very small, then the angle of deviation delta equal to a into mu minus 1. It is derived from the prism formula. Prism formula is mu equal to sin a plus dm by 2 divided by sin a by 2. So here is the angle of prism. Previously I was already discussed mu v greater than mu r. If mu v greater than mu r, from this formula delta is directly proportional to mu. So if mu is greater than delta also greater. So hence violet light will greater deviation than the red color. So delta v greater than delta r. So other colors deviates through angle between delta v and delta r. This is the wavelength, highest wavelength of red color, lowest wavelength of violet color. So other colors are deviated angle between violet and red deviation. So according to their wavelength, yellow light is called having refractive index mu y equal to mu v plus mu r by 2. Then next one is the angular dispersion. What is angular dispersion? Angular dispersion for any two colors. It is defined as the difference between angle of deviation suffered by two colors while passing through the prism. If the white light is passing through the prism, then it will be converted into 7 constituent colors. So this is the difference between angle of deviation between any two colors. But in this case, I will be consider red and violet. So first we consider a small angle prism with angle theta, with angle A. Theta is the angle of deviation between two colors, red and violet. This is the angular dispersion. So angle of deviation, let delta v and delta r be the deviation for violet and red rays respectively. Then the angular dispersion for violet and red is given by theta equal to delta v minus delta r. But for violet ray, from this formula, delta is converted into delta v, mu is converted into mu v. So delta v equal to a into mu v minus 1. Similar case for red color, delta r equal to a into mu r minus 1. So putting this value in this equation, so we get theta equal to, theta is the angular dispersion, theta equal to delta v minus delta r equal to delta v, putting the value of delta v and delta r. The value of delta v is a into mu v minus 1 minus delta r value is a into mu r minus 1. So equal to a into mu v minus mu r. So अतः delta v minus delta r equal to a into mu v minus mu r. Now next one is the dispersive power. It is also between any two colors. Is defined as the ratio of angular dispersion for these two colors to the deviation suffered by mean light. If we consider the violet light and red light, then the angular dispersion is delta v minus delta r, and the angular deviation is delta. So dispersive power omega equal to delta V minus delta R by delta. We also know that if delta V minus delta R is the angular dispersion for violet and red rays, and delta is the deviation suffered by mean light, then the dispersive power of the material is omega equal to delta V minus delta R by delta. But if the mu is the refractive index of the material of the prism for mean light, then the deviation, angle of deviation for mean light is delta equal to A into mu minus 1. Putting this value in above equation, we get omega equal to A into mu minus 1 divided by A into mu V minus mu R divided by A into mu minus 1. So I cancel, we get omega equal to mu V minus mu R whole divided by mu minus 1. So the next one is the refraction through a thick lens. So the optical system is thick lens. So first we consider a thick lens of thickness is small t, and the material having refractive index is mu m. Then the other side refractive index is mu 1. But inside the thick lens, the refractive index is mu 2. So the thick lens have two radii of two surfaces, 1 and 2 respectively. So in this case, the ray passing through the lens suffer two refractions. Because two surfaces are there, so refraction also, two refractions are there. So one from first surface, then another from second surface. If the radius of curvature is R1 for first surfaces and R2 with the radius of curvature for second surfaces, then one translation through a distance d in the medium of refractive index is mu. Here we consider mu 0 equal to mu I equal to mu 1, so mu equal to mu 2. So systometrics for thick lenses we also previously discussed, but in this case simply SM thick equal to RM2 TM2 RM1. This is the equation number 1, where RM1 and RM2 are the refraction matrices. TM1 is the translation matrix. So this is the value of RM1 and RM2 and also TM2. RM1 equal to 1 0 1 by R1 into mu 1 by mu 2 minus 1 mu 1 by mu 2. RM2 also 1 0 1 by R2 mu 2 by mu 1 minus 1 mu 2 by mu 1. TM2 also 1 3 0 1. So putting the value of RM1, RM2, TM2 in equation 1. So systometrics SM thick for thick lens equal to, putting these values, so there are three matrices. So first we consider, fix the first matrix, then multiply the next two matrices. So there are two rows and two columns. First row, first column, first row, second row, first column, second column. Similar case of third matrix. So how to multiply? So first first row, first column, first row, first column, first row, second column, second row, first column, second row, second column. So first matrix is fixed. Then next one is how to multiply first row, first column. So 1 into 1 plus t into 1 by R1 into mu 1 by mu 2 minus 1. This is the case. Then next one is first row, second column, 1 into 0 plus t into mu 1 by mu 2. This is the value. 0 plus this is value the t mu1 by mu2. Then the next one is second row first column 0 into 1 plus 1 into 1 by r1 into mu1 by mu2 minus 1. This is the value 1 by r1 into mu1 by mu2 minus 1. Then the next one is second row second column 0 into 0 plus 1 into mu1 by mu2, so it is also known as mu1 by mu2. Now look at this is the two matrices. So in the previous case we also multiplied first row first column, first row second column, second row first column, second row second column. So first one is 1 into this plus 0 into this. So we get 1 plus t by r1 into mu1 by mu2 minus 1. The next one is first row second column 1 into this, the value is t into mu1 by mu2 plus 0 into this, 0 into this is value is 0. So now the total value is t mu1 by mu2. Then the next one is second row first column. So 1 by r2 into mu2 by mu1 minus 1 into 1 plus t by r1 into mu1 by mu2 minus 1 plus mu2 by mu1 into 1 by r1 into mu1 by mu2 minus 1. Then the next one is second row second column 1 by r2 into mu2 by mu1 minus 1 into t into mu1 by mu2 plus mu2 by mu1 into mu1 by mu2. These are cancelled, so the value is 1. This is the value. This is the equation number 3. Let us consider if the medium on the both sides of optical system is same. If we consider the optical system in this case, look at the systems. If these sides are equal, so one by f equal to minus c. So focal length of the system is given by 1 by f equal to the minus c, where c is the elements of the system matrix equal to a, b, c, d. So putting this value, then we get a, b minus 1 by f d. So equating this equation with third equation, then we get the value of c. So the c value is minus 1 by f. So minus 1 by f value is this 1 by r2 into mu2 by mu1 minus 1 into 1 plus t by r1 into mu1 mu2 minus 1 plus mu2 by mu1 r1 into mu1 mu2 minus 1. This is the value. So minus 1 by f equal to the value is 1 by r2 into mu2 by mu1 minus 1 into 1 plus t by r1 into mu1 by mu2 minus 1. But in this case, the mu2 by mu1 is multiplied with this term. So we get 1 by r1 into this value is 1. So 1 minus this value is mu2 by mu1. So equal to 1 by r2 into mu2 by mu1 minus 1 into the same value. So changing this value, so we get minus sign is outside from the bracket. So we get minus 1 by r1 into mu2 by mu1 minus 1. So taking common to the right hand side of these terms, mu2 by mu1 minus 1. After taking common the value of mu2 by mu1 minus 1, then we get in this case 1 by r2 minus 1 by r1 plus this is the value t by r1 r2 into mu1 by mu2 minus 1. This is the value of 6. Put the value mu2 by mu1 equal to mu. then the equation number 6 becomes, this is the value of mu, so minus 1 by f into mu minus 1 into 1 by r2 minus 1 by r1 plus t by r1 r2 into 1 by mu minus 1. So this is the value. So 1 by f equal to, taking both sides negative sign, so we get 1 by f equal to mu minus 1. So changing the signs, so if we taking the negative sign, then the first positive term is 1 by r1 minus 1 by r2 minus t by r1 r2 into 1 by mu minus 1. So 1 by f equal to mu minus 1 into 1 by r1 minus 1 by r2 minus t by r1 r2 into this value is 1 by 1 minus mu by mu. So after taking the negative sign from this bracket, so we get negative negative is positive, so t by r1 r2 into mu minus 1 by mu. This is the equation number 7. So special cases, if the optical system is thin lens, that means the thickness is 0, so t equal to 0. Putting the value of t equal to 0 in equation 7, we get 1 by f equal to mu minus 1 into 1 by r1 minus 1 by r2. Thank you.